In this video, I'm going to show the image of why you need supply-independent biasing with a proper setup. From the white current mirror video, we've known that the current accuracy is very important to provide a well-defined DC operating point for a CML amplifier or any other analog circuitry. Therefore, we should apply a current meter and distribute the meter current IR as an IC bias current here, if there is a precision current reference IP available. But we never talk about where this precision or reference current came from. Let's dive into the image of the precision current now. This image, the reference current using resistor, will provide a simple and intuitive way of generating the reference current, which is well defined by the size of the resistor R1 and transistor M1 together. But do you see any impairment here? Think about the supply noise image for 5 seconds. Correct. As you can see, the supply voltage will vary the overdrive voltage of the M1 and the voltage across the resistor. Therefore, the supply noise will modulate the current and generate the noise in the reference current. Think about your own supply noise image now. If the supply VDD is increased by 10 mV, then the current will be increased by 10 mV divided by the resistor R1 in series with the transistor impedance 1/GM1. On the other hand, if the supply VDD is decreased by 10 mV, then the current will be decreased by 10 mV divided by the resistor R1 in series with the transistor impedance 1/GM1. So, what can we do? Think about a recursive images for 5 seconds. Bingo! Our recursive meter idea is to assume one reference IREF to meter and bias another branch IR, and another branch IR could be a reference to meter and bias back to original branch IREF. The recursive mirroring image is to IR is independent of the supply VDD, since the IR was mirrored by an IREF as we discussed in the white current mirror video. Then, if IREF could be a replica of IR, then the IREF would be supply independent biasing as the IR owing to the mirroring advantage. The IR can be M times IREF if the device size ratio is an M with no channel length modulation effect or mismatch here. Another image is those diode M3 were connected to the current source device M2 and M4. Therefore, the IR or IREF should be relatively independent of the supply variation or noise. But be careful about the subtle images here. If the current is only defined by one equation, IR equals M times IREF, the current is arbitrary and not well defined actually. So this configuration will not work and still miss one constraint. What can we do? Think about the source degeneration images for 5 seconds. Great. We could add a source degeneration to the source current source, which provides negative feedback and stabilizes the biasing as we've known from Microelectronics 101. So, the diode connected M1 will meter the current to the M2, and both IR and IREF are equal. The device size of the M2 must be bigger than the M21 for sure, which is K times the size of M1 in this image due to the overdrive of M2 being degenerated by the source resistor's Is. In addition, both device size of the M3 and M4 must be the same, since the current IR of the diode connected M3 should mirror the current IR back to the M4 without any source deviation resistor. The operation image will not only show the size of the 4 devices, but also identify the 2 defined equations. IR equals IREF. VGS1 equals VGS2 plus IR times RS. Then you should have a clear image that the current is independent of the supply voltage, but will still depend on the process and temperature. To be clear, there's no VDD in the 2 equations, but the VGS and RS still depend on process and temperature, since the active and passive devices process and temperature dependency. Even so, this supply-independent biasing image is the most popular topology people use in the industry. However, it's not complete yet. Could you think of the startup images for 5 seconds? Correct. When the system is powered down, the current in the system, including the bus current, should be 0, which is correct and hold here from both equations. What happens when the system is powered on, which is called startup state? Unfortunately, the supply-independent biasing will still be in silent state, which we call a dead zone in a steady state here. Again, IR equals IREF equals 0, and VGS1 equals VGS2, while IR equals 0 holds the startup state as the power down state. So, what can we do? Think about a non-steady state images for 5 seconds. Bingo! We need to add a startup circuit to help biasing away from the steady state, which will be a simple trigger. The M5 diode connected here will start a current. The VDD was ramping up from 0 volt to 1 volt, for example. But do you see any constraint to starting this current? Think about the turn-on images for the current path. Correct. Only M3, M5, and M1 must be turned on. Therefore, the sum of those 3 voltages must be less than the supply voltage VDD. On the other hand, the supply voltage must be greater than the sum of those 3 things to make this startup topology work. Besides the startup constraint for a non-steady state trigger event, what else could be the issue? Great. What happens if the startup circuit stays turning on? Then you should have the disturbance image from the startup. In a normal operation, the current flowing should be at the left IREF and the right IR branch. But the trigger current I startup will disturb both IREF and IR with a varying current from time to time. Then the biasing current IR will have lots of interference current on top of its DC current. Therefore, another constraint of the sum of the gate source voltage of M1 and VGS1 plus VGS3 must be very close to the supply voltage VDD with a slightly smaller than the M5 threshold voltage VTH5, such that the M5 should turn off after the IR equals IR in a steady state. Please be advised that the M5 as a trigger current branch for a startup is just an example here, and there are lots of different creative ways of adding the startup circuit. You can try your own startup circuit image. Here are the summarized image of why you need a supply-independent biasing with a proper startup to provide a precise and well-defined current in a convenient way. the current meter is a must, but the reference current may be noisy since it could suffer from supply noise. To tolerate a higher supply noise without breaking the quality of the reference current, a supply-independent biasing is a must. However, there is a dead zone in the steady state that both IREF and IR current would stay zero even though the supply is powered on. Therefore, a trigger current by adding a startup circuit is a must. Of course, the trigger current should only sink current from the supply to the ground during the power on transition state, not the normal operation steady state. The startup must be turned off properly after its proper startup to avoid interrupting the normal operation. The whole image once again summarizes why you need a supply-independent biasing with a proper startup. Thanks for watching. Before you go, if you are benefiting from those circuit images, I would love to hear your feedback, and please share your comments down below. Lastly, please share the video link with the people who may be banned from it.